Welcome everyone. In this video, we will solve a problem based on the Mosfet, a small signal model and its operation, and it is from the Microelectronics circuits book. So the question is for the amplifier design. For the amplifier design, okay, a circuit is given which is shown here, okay, with VDD 5 volt, RD, RD is also given. This RD is given 10 kilo ohm. Threshold voltage 1 volt, mu n COX 20 microampere per volt square, aspect ratio 20 W by F, VGS get to source voltage, the DC get to source voltage 2 volt, and channel length modulation we have to neglect. So the first thing we have to find find the DC voltage and DC current, that is our ID, drain current ID, and voltage, drain voltage VD, okay, that we have to find DC1, okay. Then we have to find the transconductance parameter, that is our GM, okay. Then after we have to find the voltage gain AB V naught by VI, that we will solve. Then after we have to find for VGS 0.2, okay, 0.2 sin omega t, we have to find AC drain voltage, okay, and what is the maximum and minimum value of VD, okay, that we have to find. And finally we have to find the various component of ID, and also we have to, after calculating the various component of ID, that is our instantaneous, I will tell what is the symbol representation, and express the amplitude, okay, we have to express the amplitude of the second harmonic component as a percentage of the amplitude of the fundamental. So that three, four things, five things we have to find. So basically, this one is also, this question will also include the ACA small signal model also. So the very first thing is we have to find number A portion. Okay. So very first thing we have to find what ID, the DC value of the drain current, and VD. Okay, so we have to find the drain current. Okay, so before that, this one is the representation. For representation point of view, I want to share, if VGS means both symbol, okay, like for the symbol I am saying capital V here, and subscript, that is our small gs is in, or better to write R in a small letter, R in a small letters, okay, this kind of notation you have to know. So this one is basically AC signal, where both V as well as GS both will be in the a small letter. Now one both is in the capital letter, we are saying this one is a DC signal kind of thing, DC get to source voltage. Now one more representation, V small and GS, so this one is our instantaneous get to source voltage. Here I am saying instantaneous get to source voltage, get to source voltage. So this notation we have to know, okay, it is very important. Again I am highlighting, when this VGS both symbol as well as subscript in the small letters, so it is SC, both capital DC1, instantaneous symbol capital, subscript sorry, symbol small and subscript capital, this one is our instantaneous, okay, instantaneous get to source voltage. And that instantaneous one I am writing here, the if we apply KVL in this loop, okay, by applying KVL in this loop, okay, say loop 1, the instantaneous one VGS is always AC component plus DC component, that we have to know, and it is from the microelectronics book, a very standard book. So this we have to know, means so from here also we can examine that This VGS means when we are giving the small signal model, means AC signal like zero point 0.2 sin omega t, so AC1. Okay. VD means we have to find the DC drain voltage, DC drain current. Okay. Then VD is the AC voltage, AC drain voltage. Okay. ID, capital D, so instantaneous drain voltage, that we have to find, that we will discuss later. So this is the simple notation, but you have to be very careful about notation. Now we have to find ID and VD. So this one is the circuit. So basically we have to go for the AC analysis. Oh sorry, DC analysis. So I'm redoing the same circuit. Okay, so I have already made the circuit. So for the DC analysis, what I am doing, we have to replace, or we have to sort the AC signal. Okay, so directly we are just putting only the gate to source voltage. Okay, now this voltage is our DC drain to, sorry, we have to find the DC one. So this voltage we have to write it VD, and this RD value is known to us, that is our 10 kilo ohm in the question. So this one is the DC. For the DC analysis, we are replacing this K2 source and doing the DC analysis. So now we have to find the drain current also, ID. So which region we have to prefer, either saturation or linear. So in the question it is very clear that for the amplifier, so for amplifier purpose, also I am writing one more line because it is very important. For any amplifier design we can write amplifier design, linear amplification, linear amplification can be obtained, can be obtained by biasing the Mosfet in such a way that it is in the saturation region. In the Mosfet, in the saturation region, in the, so this one is very important point. For the amplifier design, we have to bias the Mosfet in the saturation region, and okay, and by keeping, this one is very important line. That's why I'm writing keeping the input signal small, input signal, or a small input signal, a small value. For any amplifier design, we have to, for the amplifier design, we have to do the biasing of the MOSFET in saturation region, okay, and keeping the input signal as small, okay, for the linear amplification we can say. This is an important line. So now one can easily find the other parameter because everything is given. In given RD, VDD, VT, mu and Cx, everything W by L, okay. So one can directly write the drain current equation, okay, ID, ID. So ID we have to write in saturation region. Drain current in the saturation region. We know the formula 1 by 2 mu n COX W by L, capital VGS minus VT whole square. So this can be written as 1 by 2 mu n COX is given 20 micro. Okay, 20 it is given. Okay, once again I am sorry. 20 microampere per volt square. So I am just writing 20 into 10 to the minus 6. W by L is also given 20 into VGS. VGS is given 2 volt and VT is 1 volt. Okay, VGS is 2 volt and VT is 1 volt. So one can write 2 minus 1 whole square. So once again what we can write, this should be our 10, yes or no? Clear? And 20 and 2 minus 1, 1 square means 200, we can write directly microampere. So the ID, okay, will be simply our 200 microampere. The current will be 200 microampere. That's the first portion. Okay, now we have to find the VD. Okay, now ID is not now known to us. ID is now our, I can write here 200 microampere. Now we have to find VD. Okay, so VD expression we can very simply we can write for VD. We can write VD equals to VDD minus ID. RD. Simple calculation is there. This VD is this voltage minus the drop across this resistance minus ID RD. Okay. So very simply we can write VDD is how much? 5 volt. It is given in the question 5 volt. ID we have already calculated 200 into 10 to the minus 6 and RD value. Okay. RD we can check 10 kilo ohm. 10 into 10 to the power minus 3. So it should be 10 to the minus 3 and it should be 200. So 5 minus, simply we can say this one is 2. So this should be our 3 volt. So our VD will be 3 volt. So we have calculated the first portion of the question, VD and ID. Okay. Next, okay, this one is ID, VD. We have calculated from the DC analysis. Okay, from the DC analysis we have calculated. Now the second portion, transconductance, GM. Okay, now for B, GM we have to find the transconductor. Okay, so as we know that ID equation 1 by 2 mu n COX W by L VGS minus VT whole square. So if we differentiate the drain current with respect to VGS, it will give the transconductance parameter GM. Okay, so that can be simply 1 by 2 mu n, simple differentiation we have to do, into twice VGS minus VT, okay, into 1. Okay, so this should be cancelled out. So it should be simply mu n COX W by L VGS minus VT. So in general we can write GM mu n COX is 20 micro. Okay, W by L 20, VGS minus VT 2 minus 1. Okay, so 1 400 400 into 10 to the power minus 6. So generally the transconductance is in the millisiemens. So what we can write, 400 into 10 to the power minus 3, and if we put this 10 to the power 3 here, 10 to the power 3 here, so it will give how much? 0.4 millisiemens, or simply GM we can write it 0.4 milli ampere per watt, or 0.4 what millisiemens, anything you can write. Okay, so this one is the transconductance calculation by using this drain current equation in the saturation region. Now we have to go for the next part, that is our gain calculation. Okay, so now for the gain calculation, what we can do, voltage gain. Okay, so voltage gain means we have to go for the SE analysis. C portion, that is our voltage gain calculation. Okay, so for the voltage gain calculation, again I am just want to draw the circuit first. For the voltage gain calculation we have to go for the SE analysis. Okay, voltage gain SE analysis we have to do. Okay, so for this purpose what we will do, we will remove the DC voltages. Okay, this one is RD. Okay, RD having 10 kilo ohm. Okay, so we have to make it ground VDD, and then this should be also grounded. Okay, and this VD is simply our a small VD, or sometimes we can add the output. Okay, so what we have to do, we have to replace this Mosfet with the equivalent AC model. So what we can do, simply this one is our get in, drain in, okay, GM VGS, okay, a small VGS, clear, and this would be our grounded, and drain, no need to put R node because channel length modulation is neglected, and this from this RD will come here, RD, and this one is our V naught, we can say, or sometimes say we can say the VD, okay, and this value will be VGS, and this one is the plus of minus, this one is also the VGS, okay. So input is this, clear. So this one is the representation, means what we did, instead of this transistor we have put it this model, okay, a small signal model, clear, very simple. This representation is that. So now we have to find the voltage gain. So for the voltage gain calculation, what we can do, the V naught, V naught, for example, I am saying some current is flowing like this, GMVGS. So I am saying this one is our ID, AC one. So always I am this is the AC representation. So I small d all should be in a small letter. So ID will be, if this one is RD and this voltage I am saying V naught and some current is flowing like this ID. So it should be higher potential 0 minus V naught. Okay, better to do here. Means this ID value will be 0 minus V naught by RD. So V naught will be, so I am writing V naught equals to minus ID RD, and ID is nothing but simply our GMVGS. ID is nothing but simply our GMVGS. So V naught equals to minus ID RD, and ID is nothing but simply GMVGS. So minus GMVGS into RD. So V naught by VGS equals to minus GMRD will be the gain. Okay. So this one is the gain AV, that is our V naught by VGS, and this should be minus GM. So already we have calculated the value of GM 0.4 milli. So 10 to power minus 3 into RD value is known to us 10 kilo ohm. So better to write 10 into 10 to power 3. So this should be cancelled out. So it should be minus 4 volt by volt, or simply write minus 4. So AV value will be minus 4. Okay. So this one is the gain. So this gain we have calculated using the AC analysis. First we did the, in the very first problem, first we have to find the DC one. So DC analysis we did. Then after voltage gain, so voltage gain is also now, okay. So now we have to go for the question D portion, okay. Now D we have to find the VD, a small VD, okay. We have to find the small VD. So once again, a small VD we have to find. A small VD is nothing but simply our, a small VD is nothing but simply we have to find the V naught value. So VD is nothing but simply minus GM VGS RD. Okay, this one, this expression is also for the VD, and we are doing this as a D portion. Okay, once again I want to show D, we have to find the VD with VGS given. VGS is given. Okay, and here the VGS is given 0.2 sine omega t. Okay, so this VD will be, GM value is given, So minus 0.4 into 10 to power minus 3 millisiemens. RD value is given 10 into 10 to power 3 and VGS is now given 0.2 sine omega t. Okay, so this and this will be cancelled out. So it should be minus 0.4 into 0.2. So into 10. Into 10 is also there. So it should be around minus 0.8 sine omega t. Okay, this one is 0.4 4 into 10, 0.4 into 10 4 4 into 0.2 0.8 sine omega t. So the VD, the AC voltage across this V naught will be minus 0.8 sine omega t. Okay, that we have find. Now we have to find VD, we have find. Okay, in addition to that we have to find the maximum and minimum value of VD. Okay, so maximum and minimum value of VD we have to find. Okay, so we have to go for the next page. In D1 we have to also find the maximum and minimum value of VD. Okay, so VD we have already find this VD. Okay, in the first page VD we have find minus 0.8 sine omega t, minus 0.8 sine omega t. Okay, we have find VD. Okay, so now in the question, okay, one more thing, it will better to solve. Mm, what are the maximum and minimum values of VD, not this VD. Okay, there is some mistake. This one will be a small v, capital D. So we have to find the instantaneous one, VD. Okay, sorry, this one is the, okay, next. We have to find the maximum and minimum value of this V and D. Okay, VD. So this one is our instantaneous one. Instantaneous drain voltage. So which is basically instantaneous drain voltage will be some AC component plus DC component. So AC component we have calculated and DC one, DC VD is also we have calculated in the very first problem, which are our 3 volt. Okay, and this one is our this volt. Okay, so the AC component, it is clear. So VD will be 3 minus 0.8 sine omega t, because we have to put the value of VD as 3 and for this we have to put minus 0.8 sine omega t. So we have to find the maximum and minimum value. So okay, so VD, okay, maximum we have to find. Okay, so what we have to do, sine omega 2 value will be minus 1. If this one will be minus 1, it will be maximum 0 minus 0.10, and if this value is sine omega t is minus 1, it value will be maximum. So it should be 3 plus 0.8, 3.8 volt. Okay, and VD minimum, for VD minimum value sine omega t will be 1. So it should be 3 minus 0.8 into 1. So 3 minus 0.8, that was simply 2.2 volt. Okay. So it is very simple, means in question they are asking about the VD, instantaneous voltage, maximum voltage, minimum voltage, instantaneous, which is a combination of AC plus DC. Okay, so DC we have already calculated 3 volt and AC also we have calculated this one. So the overall will be 3 minus 0.8. Okay, now for the maximum value we have to take sin omega t minus 1. So if you put, it will come this one. Now for the minimum value sin omega t, we have to take sin omega t value 1. So we will get 2.2 volt. Okay, so this one is the D portion. Now is little bit tricky but interesting. So the final one is our E. E. Okay, so I will also show what is the question. Determine the various component of ID, means instantaneous drain voltage ID, various components. So first we have to go for the ID, means what should be the ID, various component ID, that we have to find. Okay, so for the ID value, what we will do, this ID, the instantaneous one, must have some DC component plus AC component. Okay, and this ID can be when then current in the saturation region, we can write it mu NCOX W by L. This should be VGS minus VT whole square. This one is our instantaneous get to source voltage. Instantaneous get to source voltage. Okay. Once again the diagram. Means this one, the current, this one is a RD. So the instantaneous current I capital D, that's why I capital D, the instantaneous get to source voltage V a small capital. So this VGS is nothing but simply a small VGS plus VGS, which can be easily calculated by just applying KVL in this loop, plus VGS minus VGS equals to 0. So VGS this. Okay, so this one is the expression. So now this one is the instantaneous voltage, instantaneous drain current, sorry, instantaneous drain current. So now ID can be written as 1 by 2 mu NCOX W by L. Instead of this, VGS plus VGS minus VT whole square, or one can simply, instead of VGS, we are writing this DC part plus AC part. 1 by 2 mu NCOX W by L. In bracket, one can write also VGS minus VT minus AC component. Is it okay? Clear now? Means, okay, like this. Now, one more thing. There is a square term, so make it a square. Okay. So ID value will be 1 by 2 mu n COX W by L. In bracket, what we can write, VGS minus VT whole square plus V square GS plus twice times of VGS minus VT into VGS. Is a very good problem. Okay, this is very good. Means you have to very careful about all other parameter, everything. So this ID value can be written as 1 by 2 mu n COX W by L. Now I am just VT all square plus 1 by 2 mu n COX W by L V VGS square plus 2 will be cancelled out, mu n COX W by L, mu n COX W by L, 2 cancel, VGS minus VT into a small VGS. Okay, now what we can write, ID. The first term is simply our DC component. So ID plus 1 by 2 mu n COX. Okay, I am writing each and every step, plus mu n COX W by L VGS minus VT into VGS. Okay, this one. So now we have to solve the exact value of ID. Okay, the instantaneous one. So I'm selecting some different color. So ID DC1 we have already calculated. I have remembered the value 200 microampere. So I writing 200 micro. Then 1 by 2 mu n COX is 20 micro. So 10 to 10 to the power minus 6. Okay. W by L is also 20. So now I am writing 20. VGS is 0.2 sine omega t whole square. So I am writing because VGS value is given, the AC value is 0.2 sine omega t. So just writing like this. Okay. Then again plus term mu and COX 20 into 10 to the power minus 6 into 20 VGS minus VT. VGS is 2, VT is get to source, then get to source voltage will be 2, DC1 minus 1 VT, VGS into, we have to very careful about that all calculation. So next again 200 micro, so make it micro, this will be 10. Okay, then okay, one can also write 10 to the minus 6, then 20, 0.2 into 0.2 into sine square omega t. Okay, then 2 minus 1, then it should be 400 into 10 to the minus 6 into 0.2 sine omega t. Okay, go step by step because if I skip some point there will be mistake. 200 micro plus, now if you have to solve 0.2 0.2, so suppose I am removing these two decimals, so it should be 100. So this zero cancel, this zero cancel, 2 to 4, 2 4, 4 into 2 8. So 8 into 10 to the minus 6. Okay, one more line I will write after that. Sin square omega t plus 0.2. If you remove this decimal 10, so 40 into 2 80. 80 into 10 to the minus 6 sin omega t. Okay, so ID value, one is common, micro is common here, this one is micro is common, micro, micro. Okay, so can I make it out? Okay, so 200 plus 8 and sine square omega t can be the 1 minus cos 2 omega t. Okay, sine square omega t will be our this one 2. Okay, is any mistake? 2 into 20. 20 into, okay, there is some mistake, it should be 4. Okay, yeah, means okay, wait, I'm just again doing. Okay, means 2 1 by 2 into 10. Okay, 20 into 0.2 into 0.2. Okay, so it should be our 10 into 10. Okay, 10. Okay, so is any mistake? 1 by 2 into 20 into 10 to the power minus 6 into 20. Okay, so 2. Okay, so if we solve, it will come 200 micro plus 4, and this will be 1 minus cos 2 omega t in microampere. Okay, plus this should be, you just check, there is some 4 into 2 means 40 into 280 sine omega t into 1 microterm will be there. So if we solve this one, it will come like this: 200 plus 4 minus 4 cos 2 omega t plus 80 sin omega t micro. Okay, so id value will be 204 plus 80 sin omega t minus 4 cos 2 omega t. Okay, and it is in the microampere. This one is the answer. Okay, id component. So now in the question also we have to find the determine the various component of id. So we have find and express the amplitude of the second harmonic component as a percentage of the amplitude of the fundamental one. So the f portion, so the f portion from this one, we have to second harmonic amplitude in the question, second harmonic amplitude by fundamental harmonic amplitude. They are asking into 100, we have to write. So second one is 4. Okay, amplitude 4, fundamental one is 80. No need to write to 204, but we have to go for the s into 100. Okay, so like that it should be 20, then 5, so 5%. Okay, so this is all about this question. Okay, so there may be some mistake in this calculation, but you have to very careful, it will come like this. Okay, so this is all about this question. We have find the dc value dc value of the drain voltage and current id. Okay, then gain also, transconductance, ac drain voltage, maximum minimum value of the instantaneous drain voltage, various component of the id, and the amplitude of the second harmonic component as a percentage of the amplitude of the fundamental we have also calculated. So this is all about this video. So thank you for watching this video.